Good morning, everybody. We will continue today our treatment of physical systems, and specifically we'll deal with grand canonical ensemble. We have seen last lecture that for the grand canonical ensemble, the partition function and the probabilities are described by the following equation. F is 1 over z, where z is a partition function, e to the power minus beta epsilon I minus mu ni. Okay, so notice instead of having only one parameter, like the temperature or the beta, we have two. The chemical potential mu and the beta. They define the parameters of the system. The partition, so this is the probability. The z is the partition function. Which is a summation over all of I, e to the power minus beta epsilon I minus mu ni. Okay. We know that for the grand canonical ensemble, the energies or the energy of the system is not constant, and the number of particles of the system is also not constant. So mu I, oh no, not mu, epsilon I, energy of state I, Ni is the number of particles of state I. So this is the microscopical description of the grand canonical ensemble. Temperature defines beta, chemical potential defines mu, which is exactly mu, right? The energies and the number of particles for each state are undefined, and this is the microscopical description. How we connect this microscopical description to something which is macroscopical or thermodynamical. So we know that there is, for each ensemble there is a thermodynamical potential that is associated with this ensemble. Okay, specifically for the canonical ensemble, this was the Helmholtz free energy. Okay? Now for the grand canonical ensemble, we have shown that the thermodynamical potential it is the grand canonical energy, or grand canonical potential, which is E minus Ts minus mu n. Okay? And how you connect this description and the thermodynamical potential, which is the grand canonical potential. This is the grand canonical potential. Right. The connection is very simple, and it works in the same way for any connection between the ensembles, the microscopical description of the ensemble, and the thermodynamical potentials, which is psi equals minus 1 over beta log of v. And that's it. With the moment that you know psi, you can obtain any variable, average variable, by making an appropriate derivatives, by taking appropriate derivatives of this specific grand canonical potential. We'll see that in a second. Great. So we have those two descriptions. Now let's us focus on why we developed this. Okay. So remember, the problem that we started with is constant n. Okay. For any system that is described by the grand canonical ensemble, the number of particles is not conserved in the system. Okay? Very similar to the situation that for canonical ensemble, the energy is not conserved. Okay? There is an exchange of particles or the exchange of energy. Why we have done this trick? Okay? So this trick was performed in order to avoid cumbersome combinatorial calculations. Okay? Specifically, those calculations are unavoidable when you treat quantum particles. Because in quantum statistics, there is always the Pauli exclusion principle, and the Pauli exclusion principle is an extremely strong interaction that you cannot just simply swipe under the rug. Okay. So let's see the specific system that I already told you that we will start with. So, quantum statistics. Simple example. All right. So what do we have? Our system have exactly 3 energetic levels. So this is our energetic spectrum. I don't know what this axis means, but actually what we have is epsilon 1, we have epsilon 2, and we have epsilon 3. Okay. So those are the 3 states. Those are the 3 states. Epsilon 1 is the ground state, and there are excited states, epsilon 2 and epsilon 3. For now, let's forget that there are any other possible states. Above epsilon 3, we only focus on these 3 states. Okay, now, we are going to deal for this example with fermions. Fermions. Okay, so the Pauli exclusion principle states the following. If we put one single particle and we know it spins, let's consider the specific situation that the spins can be 1/2 and -1/2, okay, or fine. Then we don't really, we can look on them just like up and down. The moment that we have one single particle on this specific state, we cannot put another particle in the same state. Okay. That is forbidden. Okay. This is the Pauli exclusion principle. You cannot do this, and this is why we look on the situation where we have different ni's and epsilon i's. So how we are going to address it? Everything in statistical physics is related to computing this partition function. The moment that you know partition function, you can calculate the probabilities, you can calculate whatever you want, you know the partition function, you can calculate the ground canonical potential, etc., etc., etc. So everything is related to the partition function. However, it is defined given the ensemble. All right, so what we are going to do? The idea is, well, those 2 states are forbidden. Right? Now remember, the only trick that we know, and anybody knows, is to somehow factorize this damn thing. We don't know any other tricks but factorization. Okay? There are very small amount of examples where you can calculate the partition function without actually factorizing it, and even in those specific systems, you somehow factorize. Okay. So the problem with factorization, remember, is it depends on the following things. So first of all, the energy is what? Is sum of energies of different particles. And usually we have quote-unquote particles. Why is quote-unquote? Because those are not usually, or they don't have to be real particles, it's just sum of energies of something. Okay? So this is the first rule. Second rule, those energies of particles are independent. So in order to calculate the partition function or to reach factorization, those two conditions have to be satisfied. Okay? Summation, so the additive property, and independence. Now, the moment you have the Pauli exclusion principle, you don't have independence. It's not there, right? Why? Because I'm saying, okay, so what is the energy of my first particle? Let's assume that I can identify them, which is impossible in quantum mechanics, but let's, for example, for a moment, assume that I can identify them. Okay? I'm looking, okay, so the energy of the first particle is epsilon 1. I'm looking now on the second particle, okay, because the total energy is the sum of energies of different particles. Okay, I'm looking on the energy of the second particle, that, oh, it can't be epsilon 1. Why? Because the first particle have epsilon 1. So you don't have independence. Even for the simplest case, forget about the third level, right? Even if you have only two levels, you have this strong constraint, and this strong constraint kill independence. All right, that's it. This is why the regular approach of factorization does not work. This is why we're going to use grand canonical ensemble. Okay. Now, the cool thing is those quotes, particles. We don't need to count particles. We just need to find some entities that represent the total energy of the system. That's it. Okay? This is what we've done in Debye. This is what we've done in the polymer model. We eventually found something that we call particles. Sometimes there are not even real particles. Okay? And we use those two conditions. Okay? The same thing is going to happen over here. So what I suggest is to say, well, we are not going to use the particles perspective. We're going to use energetic states perspective. Okay. And the energetic state perspective is, for this specific example, is much more simpler. Okay. So what I'm suggesting is the following. In order to use this factorization trick, we need to satisfy those two things. Okay, so first of all, the energy of the system, total energy of the system, it is energy of state 1 plus energy of state 2 plus energy of state 3. Okay? So great. The first condition is satisfied. Now what about the second condition? What about the second condition? When I'm looking on this system, okay, so let's forget about the Pauli expression, this picture. When I'm looking on this perspective, and I'm looking on the, not on the particles, I have different perspective now, right? I'm not looking on the particles. I don't even know how many particles there are in the system, right? Because I'm in grand canonical ensemble and the number of particles is not conserved. I'm looking on epsilon 1. Does it, or epsilon 2, does it care if epsilon 1 is has a particle or not? No. It doesn't matter. Okay? It's a Fermion perspective, so either it's occupied or not occupied. It doesn't care if epsilon 3 is occupied or epsilon 1 is occupied. You absolutely don't care, right? Otherwise, the statistical, the physical perspective of the Schrodinger equation, etc., has to include those. But we change the perspective. You're not looking at the particle. This is not the identical states of the particle, or whatever. You're looking on those states. Okay? Either there is a particle or not. It doesn't care if there is a particle of epsilon 1 or epsilon 2, but you can say, but Stas, no, you have told us something that the minimal energy, and the minimal energy is important, and etc., etc., etc. So the particles will probably prefer to sit in epsilon 1 and epsilon 2, and this is not independence. And the answer is, this should be an outcome of whatever we're doing, and not something that we include in the first place in the system. Okay? So the minimal energy of the system and the preference of the particles to occupy lowest states and not excited states, it's not something that I put by hand, it's something that I obtain out of the equations. Okay? It's not an assumption, it's something that I get out. Okay? From the pure physical perspective, I have energies. Each energy is either occupied or not occupied. There is no dependence on the different states. Okay. So this is 1, this is 2 energies of different states are independent. Okay. So number 2 is satisfied as well. All right, so the moment I know this, the factorization is applicable. Factorization is applicable. The factorization is applicable. Now, what we're going to do next is, if the factorization is applicable and I'm looking on the energies of different states, okay, I can apply the perspective to each single state as if it is an independent system. I don't care if it's macroscopical, microscopical, I don't care, right? So this is the mathematics. The moment that you can factorize, you can take this each single state, right, and simply describe the partition function of each single state. Okay? So if factorization is applicable, and we're talking about fermions, the factorization tells us write down the partition function of each state. Okay. So let's see what states do we have. First, we have state with epsilon 1. So what is Z1? Z1, it is a summation over what? Of all possible states of energetic state epsilon 1. What I mean by state? Now the states is how many particles are going to sit over here, right? It is still e to the power minus beta epsilon I minus mu and I. And as in the systems where we used canonical ensemble, okay, you can shout, Stas, it's a single state. What is the temperature and what is the chemical potential? We don't care again. Why? Because factorization works. Factorization was developed as a mathematical trick. Okay? If you start with a macroscopical system where you can define what is beta and what is mu, right? Because you know what is chemical potential, what is the temperature of the system. It's a macroscopical system, so you can use it and define it. The factorization trick is a mathematical trick that tells us you take all this and you factorize, but you still keep the beta and the mu of the macroscopical system. So it's doable. Okay. So now we're going to all the different states of this first epsilon 1. So what are the different states? First state is no particles are sitting in epsilon 1. Right? So this is going to be first state. So e to the power minus beta. What is the energy of the first state if no particles are sitting over there? What? If no particles are sitting over here, what's the energy of this state? How it contributes, remember when I say energy, what is the contribution of the first state to the total energy if no particles are occupying epsilon 1? Zero, absolutely right. Okay, we continue, so it's minus mu. No particles are occupying this state, okay, multiplied by 0. So this is the first case. The second case, plus e to the power minus beta. Now we have one particle that's sitting in this state. So the energy now, or the contribution to the total energy of the first energetic state when it's occupied by one single particle is just epsilon 1 minus mu. Now it's only one single particle occupying this energetic state. It's multiplied by 1. Are there any other situations or possibilities for this energetic state? No. We counted them all, and it's very, very simple. So we obtained that it's e to the power minus beta. Oh, I'm sorry, this is just 1 plus e to the power minus beta epsilon 1 minus mu. Alright, so this is Z1. What's going to happen about Z2?
It's the same thing, but instead of epsilon 1, it's epsilon 2.
Great. The same thing happens, right? I'm going to the second state, second energetic state, and I'm saying, all right, let's write Z2. And Z2, it's a summation, all possible states of energetic state epsilon 2. E to the power minus beta epsilon I minus mu and I. Now I'm going to say, okay, so the first scenario that no particle is occupying the second energetic state. When no particles are occupying the second energetic state, the contribution, that's what's important, to the total energy is 0. So we have e to the power minus beta 0 minus mu, and no particles are sitting in this energetic state, so that's 0, plus e to the power minus beta. I put one single particle here. Okay, I put one single particle here, so there is one single particle. The energy contribution to the total energy is epsilon 2, okay, minus mu multiplied by 1. So Z2 equals to 1 plus e to the power minus beta epsilon 2 minus mu. By the same arguments, I can say that Z3 equals to 1 plus e to the power minus beta epsilon 3 minus mu. So we have Z1, Z2, and Z3. What about something else? Have we forgotten anything?
Maybe 0 and the 0?
No, there is no 0.
Ah, okay.
The ground state is epsilon 1. Okay? So you should say, all right, the partition function Z equals to Z1 to Z2 to Z3. Okay? And we have what is Z1, what is Z2, Z3. Let's write Z1 over here. Z1 is 1 plus e to the power minus beta epsilon 1 minus mu. So we have this multiplication. This is it. Anything else we should count, check, have I forgotten anything? Like my glass of water. Is it okay? Claim is not. Why not? Well, because how I stated the problem, we have fermions, and each fermion can have either spin up or spin down. Plus 1/2, minus 1/2. Okay? Now, if we don't have an external magnetic field, we have degeneracy, right? So, Pauli exclusion principle does not allow two identical particles to occupy exactly the same state. But different spins means we have different states. So, Pauli exclusion principle allows this, right? Two particles can occupy the same state, they just have different spins. So, maybe whatever we have done with Z1 and Z2, all possible states of the, we should also count those additional particles here, right? We should count them. We have one particle, 0 particles, one particle with spin up, one particle with spin down, two particles with spin up and down. Okay, so here we have two contributions. Why don't we have another one and another one? Why don't we have 4 instead of 3? Why don't we have 4? Because I'm not looking on the particles, I'm looking on the states, right? And for me, I define a state of the system using all the quantum information that I have, okay? So I'm not looking on the system as if I have epsilon 1 and I can put on this epsilon 1 two particles. No, no, no. The state is defined as a specific state of the system, the energetic state. So for me, there are two energies. One epsilon with spin up, the other one epsilon 1 with spin up, the other one is epsilon 1 with spin down. So there are two energetic states, right? Okay. So in those ideas, I have energy of state 1 plus with up plus energy of state 1 with spin down. Energy of state 2 plus energy of epsilon 2 with spin down. Energy of state 3 plus energy of epsilon 3 with spin down. Those are different states. Okay?
So like 0 and 1 is like, instead of 1 particle and 0 particle, is like 0 is down and 1 is up.
Yeah. No. I'm saying that what I've tried to prescribe before, 1 over here and 1 over there for epsilon 1, it is the epsilon with up is occupied and epsilon with down is also occupied. But I don't care about those two, right? Each of them is independent from each other.
Yeah.
That's the point. You need to account for independence, right? So, and if my focus is on the states and not on the particles, just on the states, those are different situations. So here what I calculated is Z1 with spin up and Z2 with spin up and Z3 with spin up. Okay. And what should I add to this? What should I add to this is Z1 with spin down, Z2 with spin down, and Z3 with spin down. I don't focus on specific particles and use all the possible fluctuations with the different states because it's a mixture of states. And I want to create one single state. So what if it has exactly the same energy? It's a specific, those two states are different. And if I apply an external magnetic field, they will split, all right? Those are different states from the quantum perspective. So I have to treat each of them separately. Now, the point is that due to the situation epsilon 1 up equals to epsilon 1 down, and epsilon 2 up equals to epsilon 2 down, and epsilon 3 up equals to epsilon 3 down, okay? I know that z1 up equals to z1 down, and z2 up equals to z2 down, and z3 up equals to z3 down, because I have this degeneracy. So how the degeneracy enters my factorization scheme? Z is z1 up, z2 up, z3 up, and the degeneracy is just the power of the partition function. z1 up to the power of 2, z2 up to the power of 2, and z3 up to the power not of 3, sorry, 2, to obtain that the partition function z equals to z1, z2, and z3 up, up, up to the power of 2. This is where degeneracy belongs. This is how you count. Okay? You do not count by looking on the specific energy and saying, oh, let's count the different variations of the different spins. Those are different spins. Different spins are accounted differently. For each specific state, it's a different state, and you look on the state and you calculate the possibilities of a specific state. The spin enters the definition of your state, so you can account, or you have to account, for each different state separately. Not together, not a mixture. The moment you start to mix everything, the perspective of different states disappears. This and the independence part also disappears. Remember, you have to define your states such that their occupation is independent, because your perspective, non-particles, states. Okay, so this is it. We already know what is Z2. So this is Z2 up, Z3 up, Z1 up. We know everything, and just a little bit of math is left. Okay. So what we have is z equals to 1 plus e to the power minus beta epsilon 1 minus mu 1 plus e to the power minus beta epsilon 2 minus mu 1 plus e to the power minus beta epsilon 3 minus mu, and all of this to the power of 2. Okay. Now we can ask different questions. What are the questions that we can ask? For example, what is the probability or the occupation of state 1 up? Okay. So mathematically we can address this in the nice way and in the wrong way. They're both correct, but one is neat, the other one is extremely long, and you lose a lot of time if you try to do it at home or during the exam. So what is this long way? Also correct. So you say, all right, if I need to address this thing, okay, with state up, I have to count, so what is the possibility of this specific configuration. Right? So this possibility of this specific configuration, I know the Z. I know what is the probabilities. They are defined by very specific grand canonical perspective. Okay. So this is epsilon 1, this is epsilon 2, this is epsilon 3. Okay. I should put one particle over here. It's going to be up. Okay? And I should count all the different configurations that come with this specific state 1, right? Because what I know the following. Fi equals to e to the power minus beta epsilon I minus mu n I. Now don't make a mistake, 1 over z. This is where I write epsilon I over here. This is the specific different state, okay? Not the ground state, but let's write it separated as EI. So EI, this is the energy. Now, spin up contributes to what configuration? When level epsilon 1 is occupied and level epsilon 2 and epsilon 3 is not occupied. But it also can occur in a situation epsilon 1, epsilon 2, and epsilon 3 when epsilon 1 is occupied and also epsilon 3 is occupied. So when you calculate the probabilities, right, you should sum up over all the different situations, right, over all the different situations when this occupation of the lowest possible energy comes inside. So it's not just one specific state, it's a summation of all the different states, this state, and also possibly this state, right? You have to sum up. Yes? No. It's even simpler than that. It's even simpler than that. Why? They're independent, right? So we started with this perspective of independence. So when I'm looking on this description, I'm saying, oh, but I don't need all those because I had the state perspective, right? I had the state perspective. Instead of looking on this from the perspective of what? Of the whole states that I have inside my system, okay? I can say, well, Stas, forget about it. Completely forget about it. Why? Because if they are all independent, the states are independent, Fi is going to be probability of a state. With energy epsilon 1. So what is going to happen? It is 1 over Zi, or let's write it C epsilon 1, 1 over Z1, e to the power minus beta, and let's write it in the following sense. Ni epsilon 1 minus mu Ni. What is Ni? Ni, or let's write it N1, not N1. N1, it's 1. The state is occupied. 0, the state is unoccupied. Why I can do this? Because everything is independent, right? The factorization allowed me to separate everything in the perspective of different states. The states are independent, so I don't care about what happens on the other states. I don't have to sum over all the possibilities. It eventually has to give me exactly the same result. but it's a very long way to sum over different possibilities, right? Let's focus just on this state. We care about this, and that's all. Okay? So what is the occupation probability of state 1? The occupation probability of state 1 is the situation where this n1 equals to 1. The probability that state epsilon 1 is occupied is 1 over z1 e to the power minus beta epsilon 1 minus mu. And the probability that the state is unoccupied is e to the power minus beta 0 multiplied by epsilon 1 minus mu multiplied by 0 divided by z1 equals to 1 over z1. And z1 is 1 plus e to the power minus beta epsilon 1 minus mu. You don't care about anything else. This grand canonical perspective of separating everything, at least for fermionics situation, different states, and focus on the different states, lets you operate on the level of the energetic state, and you don't care about the other energetic states at all. Okay, we will continue this treatment and what exactly those occupation probabilities, what we can take out of this behavior of this form and that form. We will continue this. Well, tomorrow there is no lecture, so we will continue this in a week from now. Thank you all.
מה שעשינו זה כאילו להחליף את האי-תלות של החלקיקים באי-תלות של
את התלות של החלקיקים באי-תלות של המצבים. כן, כן, בדיוק. זה הנקודה, כי אחרת אתה כל הזמן צריך לחשוב, רגע, החלקיק הזה פה יכול להיכנס, פה הוא לא יכול להיכנס, ופה הוא לא יכול להיכנס. אתה צריך לחשוב על זה, אבל המצב הוא רק, לא אכפת לו מי נמצא שם, כן?
נכון.
או שהוא ככה, או שהוא מלא או שלא, זהו.
בסדר. תודה.